Hi students. So students, I think all of you feel that when you are in lift and the lift is moving upward, your weight is a little bit increases, and when the lift is moving downward, you feel that your weight is decreases. And there is another case, you feel that your actual weight when you are in lift, and this is happens when the lift is moving with uniform velocity. The lift is moving with uniform velocity in the upward, or you may be in the downward, and in that condition you feel that your weight is the actual weight. Apparent weight is equal to the actual weight. Now question arises, why this is happens? So this is our today topic. You see, the apparent weight of a man in a lift or elevator. So once again, welcome to your QTSA channel TKG physics classes. Now we will discuss this part. Okay, so first case, you see, a man of mass m is placed on a lift, inside a lift, and there is a weight machine. So a man of mass m, so obviously the weight of the man will be m into g, and this mg is directed vertically downward direction. So write it for the first condition, a body of mass m, then its weight W is equal to mg, mass into acceleration due to gravity, and it is directed vertically downward, so its direction is downward. So the weight which acts on that weight machine, that is equal to mg. So obviously the weight machine also offers some resistance, also offers some force which is exactly equal to the direction of weight of the body. That is, the weight machine exert a force which is named as normal reaction force. So you write here normal reaction force, which is named in the symbol of N or R. And the normal reaction force is directed exactly opposite direction of the weight of the man. Here W equal to mg, which is directed downward, and normal reaction force is upward. And this normal reaction force is named as apparent force. The force that felt by the man is called the apparent force. The force which exerted, which measured the weight machine, exerted by the weight machine, is the apparent force. So here we will measure the value of R, and W equal to mg. This is the actual force. Now you use first condition. So our first condition, when the lift is moving upwards with acceleration a, you see our first figure shows this one, the lift is moving upward with acceleration a. So here weight of the man, first case, weight of man, it's maybe woman also, W is equal to mg, and normal reaction force which is directed vertically upward, write it, normal reaction force that is equal to R. This one is downward direction and this one is upward direction. So there are two forces, W equal to mg, which is downward, and R, that is upward. Now the lift is moving with upward direction with an acceleration a. So obviously this R will be more than mg. That's why the lift is moving upward. So here we will find the net force. The net force F is equal to here R minus of mg. This is the net force. As the lift is moving upward, when the lift is moving downward, we use the mg is more than R. So here you know the value of F, that is ma, R minus of mg. From here you can find the value of R, that is ma plus of mg. You take a common ma plus of g. So this is the value of R when the lift is moving upward direction, and this is the apparent weight that felt by the man. The weight that felt by the man is called the apparent weight. Here R apparent weight is equal to ma plus of mg. Mg is the actual weight. There is a addition part, that is ma. That's why the man feel that the weight of the man is increases. So our first condition, when the lift is moving upward, the weight of the man is increases. Okay. Now second condition, write it. Lift is moving downward direction with acceleration same, that is a. The lift is moving downward direction with an acceleration a. Now you see second case. So first of all, weight, that is mg, which is directed along the center of gravity of the man, downward direction vertically, and there is a opposite force which is exactly opposite direction of w, which is named as normal direction force r, and the lift is moving in the downward direction with an acceleration a. So obviously here also two forces act, that is mg and r, but the lift is moving in the downward direction. So the net force acting on that case, obviously mg minus r. That's why the lift is moving in the downward direction. mg is more than r. So write it for here. For this case, net force F is equal to mg minus of r. Now you find the value of r, that is ma minus of mg into r. So r is equal to mg minus of ma. So m common, that is g minus of a. You see the value of r. Yes, the value of r, that is mg minus of ma. Your actual weight mg, but there is a minus part ma. That's why the man feel that the weight of the man is decreases. So this was second case. Now we will use another case, that is case number 3 is important. Okay, so write case number 3. And case number 3, that means the lift is under rest or is moving upward or downward. Write it. The lift is at rest or moving maybe upwards or downwards with uniform velocity. That means velocity fixed, uniform velocity. So in third case, you see here w, that is directed vertically downward, w is equal to mg, and there is a normal reaction force which is directed vertically upward, which is named as r, and the lift is under rest condition, acceleration 0. The lift is under rest condition, that is acceleration 0. So when the lift is under rest condition, the net force will be r is equal to r minus of mg. You can write mg minus of r. Here net force F is equal to r minus of mg, or you can write mg minus of r also. But you see acceleration 0, that is F equal to m into a, that is r minus of mg. So a 0, that means r minus of mg, that is 0, and here you can say r is equal to mg, that is the apparent weight of the man is exactly equal to mg, that is the actual weight of the man. So here we can write apparent weight is equal to actual weight, and this happens when the lift is under rest condition. Now see, when the lift is moving upward and downward direction with uniform velocity, that means velocity constant, and you know velocity constant, and a is equal to dv by dt, that is d dt of v, and velocity is a constant, so constant differentiation 0. So when velocity constant, the acceleration, that is 0. Acceleration is 0. Now when the lift is moving upward, so in that case the net force F will be r minus mg, upward direction, so r will be first case. And when the lift is moving in the downward, in that case we can write F equal to mg minus r. But in both cases, if that is m into a, here a 0, Why? Because the velocity is constant, uniform velocity. When a 0, we can write r minus mg is equal to 0. Same here, you can write mg minus r, that is also equal to 0. So from here you can say r equal to mg, and from here you can also say that r mg is equal to r. That is in both cases, when the lift is under rest, when the lift is moving upward and the moving downward with an uniform velocity, the actual weight of the man is equal to the apparent weight. Now another case, that is case number 4, last one, write it. So in case 4 we will discuss the freely falling. Lift is falling freely. The lift is falling freely. When this one happens? When the supporting parts of the lift is breaks, then the lift is falling, acceleration due to gravity, free falling. And in that case, when the lift is falling downward, we use the net force F, that is equal to mg minus of r. So from here you can say r is equal to which one? Okay, you explain it, ma, that is equal to mg minus of r. From here you can write r, that is equal to mg minus of ma, here mg minus of a. This is the general condition when the lift is falling in the downward direction, but here the lift is falling freely. So acceleration of the lift is exactly equal to the acceleration due to gravity. A is equal to g. Now use here g plus g minus g cancel out, so r is equal to 0. Special case, r is equal to 0. That is, the apparent weight of the man is exactly 0. The man feel that there is no weight. This is the condition which is named as weightlessness. When the acceleration of the lift and the acceleration due to gravity is exactly equal, you see A is equal to G, in that condition there is no apparent weight. Apparent weight R is equal to 0 and the man feel weightlessness. The man feel no weight. So this is our 4 cases for apparent weight of a lift, apparent weight of a man in a lift. Now let's take one example, then it will be more easier to all of you. Okay, chalo. See, this is the problem. One example, you see a body of mass 15 kg is hung by a spring balance in a lift. So here write it, mass m given, that is 15 kg. Okay. And what would be the reading of the balance when the lift is ascending with an acceleration of 2 meters per second? Ascending, that means the lift is moving upward direction. You see, the lift is moving in the upward direction. This is spring balance, the man, and the lift is moving in the upward direction with acceleration 2 meters per second square. Now here you have to find out the reading of the balance. That means you have to find out the apparent weight. You have to find out R. So first case, when A is equal to 2 meters per second square and the lift is moving ascending, that is in the upward direction, what is the formula for apparent weight? We already derived, that is R is equal to, when the lift is moving in the upward, the man feels that the weight is increases, m into g plus a. So now putting the value of m, here m 15, g, here g given, that is 10, and a, that is given 2. So this one is 15 into 12, so this one will be 180 Newton. Now you convert this Newton in kgf. You know 1 kgf, that is equal to 10 Newton. You can write 1.8 Newton exactly. So from here 1 Newton is equal to 1 by 10 kgf. So in kgf this one will be divided by 10, that means 18 kgf. Okay, so this is the first case. Now see second case. You have to find out the reading of the balance when the descending with an acceleration a is equal to 2 meters per second square. In the same case, but the lift is moving in the downward. So when a equal to 2 meters per second square and the lift is moving downward, r equal to, that is, you know the formula, r equal to mg minus of a. that is AM 15, G 10, A 12, sorry 2. So this one is 15 into 8, and 15 into 8, you know the value of 15 into 8, that is 120 Newton. So if we convert in kgf, so this one will be 12 kgf. Now case number 3. In case 3, the descending with a constant velocity. Constant velocity, that means you know the actual weight is equal to the apparent weight. So for third case, velocity given v 2 meter per second square, that is uniform velocity meter per second. So r is exactly equal to the weight of the man, that is mg. Here am 15 and g is 10. So this one is 150 Newton, or you can say 15 kgf. In this way you can solve these types of problem. Now go back to your exercise book, solve it. Today I'm ending here. Bye bye.